Look up at the night sky on a clear, dark evening, far from the glow of city lights. You'll see stars scattered across the darkness, thousands of them, if conditions are perfect, each one a pinpoint of light against the black. They seem random, don't they? Sprinkled across the sky with no obvious pattern, no clear organization. Some areas are densely packed with stars. Others are relatively empty. But it all looks essentially random, like someone threw diamonds into the air and let them fall wherever they landed. But what if I told you that's not true? What if the universe has a hidden structure, a grand cosmic architecture that organizes everything on the largest scales imaginable? What if galaxies, those vast collections of hundreds of billions of stars, aren't scattered randomly through space but are arranged in a specific pattern, a structure so enormous that we can't see it from our vantage point inside it? If you're new here, welcome to the Sleepless Astronaut channel, where we explore the deepest mysteries of the cosmos together as you drift peacefully toward sleep. If you enjoy these journeys through space and time, consider subscribing so you never miss an exploration of the universe's most profound secrets. Tonight we're going to discover something remarkable, something that changes how we see the universe and our place in it. We're going to learn about the hidden structure of the cosmos, a pattern woven through space on scales so vast that it took decades to discover, and we're going to understand that we're living inside this structure right now, embedded in it, part of it, without most people ever knowing it exists. So settle in wherever you are, get comfortable, let your body relax completely. We're about to reveal one of the universe's best-kept secrets, and as we explore it together, you're going to feel a sense of wonder and peace, understanding your connection to the largest structures in existence. When you look at the night sky with your naked eyes, you're seeing stars, thousands of them in our own Milky Way galaxy, each one a distant sun, many of them with their own planets orbiting in the darkness. The stars form familiar patterns we call constellations, shapes that ancient people saw and named, patterns that have guided travelers and inspired stories for thousands of years. These constellations have been known to humanity for as long as we've been looking up. The ancient Babylonians charted the stars and gave names to patterns they saw. The Greeks inherited these patterns and added their own stories. Their myths of heroes and monsters and gods played out across the heavens. Different cultures around the world saw different patterns in the same stars, each one finding meaning and order in the scattered points of light. But stars are just the beginning of what exists in the night sky. Between the stars, invisible to your naked eyes, are other galaxies. Not just a few, but billions of them scattered throughout space, each one containing billions or hundreds of billions of stars. These galaxies are so far away that even the nearest large galaxy, Andromeda, appears as just a faint smudge of light, barely visible on the darkest nights. Most galaxies are completely invisible without powerful telescopes, but they're there, filling the universe in every direction you look, outnumbering the stars you can see by factors of millions or billions. For a very long time, for most of human history in fact, we didn't know galaxies existed at all. The fuzzy patches of light that turned out to be distant galaxies were thought to be clouds of gas within our own Milky Way, nebulae where stars might be forming. It wasn't until the 20th century that we realized the true nature of these objects and understood just how vast the universe really is. And once astronomers realized that galaxies existed, once they understood that the universe was filled with these island universes scattered through space, the natural next question was, how are they distributed? Are they scattered randomly, or is there some pattern, some organization to their arrangement? For decades, the assumption was that galaxies were more or less randomly distributed through space. Sure, astronomers noticed early on that galaxies tended to cluster together in groups. Our own Milky Way is part of what we call the local group, a small collection of about 50 galaxies, including Andromeda and several dozen smaller galaxies. And observers noticed other clusters of galaxies scattered across the sky, places where many galaxies appeared close together. But the general assumption was that on the largest scales, if you zoomed out far enough, a universe would look essentially uniform. Galaxies might cluster locally, but those clusters would be scattered randomly through space with no overall pattern. The universe, it was thought, was homogeneous and isotropic on large scales, meaning it looked roughly the same everywhere and in all directions. This assumption seemed reasonable. It fit with the cosmological principle, the idea that there's no special place in the universe, that our location isn't privileged or unique. If the universe has the same properties everywhere, then galaxies should be distributed uniformly throughout space, at least on average. But appearances can be deceiving, and sometimes the most profound discoveries in science come from realizing that what seems obvious, what everyone assumes must be true, is actually completely wrong. Let's go back in time now, back to the early days of observational astronomy, when scientists were just beginning to map the universe beyond our own galaxy. This historical journey will help us appreciate just how shocking the discovery of the universe's hidden structure really was, and how much work it took to reveal this cosmic secret. In the 1920s, as we mentioned earlier, Edwin Hubble proved that spiral nebulae were actually separate galaxies far beyond the Milky Way. This discovery opened up an entirely new field of study. If the universe contained billions of galaxies, each one a vast collection of stars, then understanding how those galaxies were distributed through space became one of the most important questions in astronomy. But mapping the universe in 3 dimensions was extraordinarily difficult with the technology available at the time. You could photograph galaxies easily enough. Point a telescope at almost any region of the sky, expose a photographic plate for long enough, and you'd see galaxies scattered across the image. But knowing where those galaxies were in 3-dimensional space, how far away each one was, that required measuring distances. And measuring distances to galaxies was hard. There were a few techniques available. If you could identify certain types of stars in a galaxy, stars whose intrinsic brightness you knew, you could measure how bright they appeared and calculate how far away they must be. This worked for nearby galaxies like Andromeda, but for more distant galaxies, individual stars were too faint to see. Another technique involved measuring the redshift of a galaxy's light. Because the universe is expanding, distant galaxies are receding from us, and their light is stretched to longer wavelengths, shifted toward the red end of the spectrum. The farther away a galaxy is, the faster it's receding, and the more its light is redshifted. So measuring redshift gives you a measure of distance. But in the early 20th century, measuring redshifts was painstaking work. You had to capture the light from a galaxy, spread it out into a spectrum showing all the different wavelengths, and then carefully measure how much the spectrum was shifted compared to laboratory standards. Each galaxy required hours of observation time on large telescopes, and there were only a handful of large telescopes in the world at the time. Progress was slow. Despite these difficulties, some astronomers began trying to map the distribution of galaxies. In the 1930s, Harlow Shapley at Harvard began a systematic survey of galaxies visible from the northern hemisphere. Shapley was a remarkable astronomer who had already revolutionized our understanding of the Milky Way by showing that the Sun wasn't at the center of our galaxy but was located in the outer regions, about 2/3 of the way from the center to the edge. Now Shapley turned his attention to the distribution of galaxies beyond the Milky Way. He and his colleagues photographed large areas of the sky, counted the galaxies they saw, and tried to understand their distribution. And what Shapley found was intriguing. Galaxies weren't distributed uniformly. Some regions of the sky showed many more galaxies than others. There seemed to be concentrations, what Shapley called clouds of galaxies. The most prominent of these clouds was in the direction of the constellation Virgo. When Shapley looked toward Virgo, he saw far more galaxies than in other directions. This concentration, which came to be called the Virgo cluster, was a massive collection of galaxies, all relatively close together in space. Shapley estimated it contained at least 500 galaxies, though later observations would show the true number was much higher, over 1,000 large galaxies, plus thousands of smaller ones. The existence of the Virgo cluster was fascinating, but it raised more questions than it answered. Was this cluster unique, or were there others like it? Were clusters of galaxies common or rare? And most importantly, were these clusters scattered randomly through space, or was there some larger pattern organizing them? Around the same time, another astronomer was making discoveries that would prove crucial to understanding the large-scale structure of the universe. Fritz Zwicky, working at the California Institute of Technology, was studying galaxy clusters in detail. Zwicky was an eccentric genius known for his unconventional ideas and his abrasive personality, but also for his remarkable insights into cosmic phenomena. Zwicky studied the Coma cluster, a massive collection of galaxies about 300 million light-years away. He measured the motions of galaxies within the cluster, calculating how fast they were moving relative to each other. And when he added up all the mass he could see in the cluster, all the stars and all the galaxies, he found something strange. The galaxies were moving too fast. Based on the visible mass in the cluster, the gravity shouldn't be strong enough to hold the galaxies together at the speeds they were moving. The cluster should be flying apart, galaxies escaping into space. But clearly the cluster was stable, held together by gravity, which meant there must be far more mass in the cluster than he could see. Zwicky proposed that the cluster must contain vast amounts of what he called dark matter, invisible material that didn't emit or absorb light, but made its presence known through gravitational effects. This was a radical idea at the time, and most astronomers were skeptical. But Zwicky was right, and his discovery of dark matter would eventually prove crucial to understanding the formation and evolution of cosmic structure. Through the 1940s and 50s, astronomers continued mapping galaxies, slowly building up a picture of the universe's large-scale structure. The work was tedious and time-consuming, but gradually more clusters were discovered and cataloged. The Virgo cluster, the Coma cluster, the Fornax cluster, the Perseus cluster, and many others, each one containing hundreds or thousands of galaxies, each one a massive concentration of matter in space. But the question remained, how were these clusters distributed? Were they scattered randomly, or was there a pattern? The answer would have to wait for better technology and more systematic surveys. The breakthrough came in the 1970s with the development of more efficient methods for measuring redshifts. New instruments called spectrographs could capture the light from multiple galaxies simultaneously, dramatically speeding up the process of measuring distances. And computers became powerful enough to handle the data analysis required to turn thousands of redshift measurements into three-dimensional maps. In 1977, astronomers at the Harvard-Smithsonian Center for Astrophysics, led by Mark Davis, John Huckra, Dave Latham, and John Tonry, began an ambitious project. They would measure the redshifts of thousands of galaxies, creating the first large-scale three-dimensional map of the universe. The project came to be known as the CFA Redshift Survey, and it would revolutionize our understanding of cosmic structure. The work began at the Smithsonian's Oak Ridge Observatory in Massachusetts, using a relatively small telescope equipped with a new spectrograph designed specifically for measuring galaxy redshifts efficiently. Night after night, the team would observe galaxies, collecting their spectra, measuring how much their light was red-shifted, calculating their distances. The work was painstaking. Each night, they might observe dozens of galaxies, but each one required careful attention. The telescope had to be pointed precisely at the galaxy. The spectrograph had to collect enough light to see the spectral features clearly. The data had to be analyzed to extract the redshift measurement. And all of this had to be done thousands of times to build up a comprehensive map. The survey focused on a specific slice of the sky, a band extending across the northern celestial hemisphere. Within this slice, they would measure the redshift of every galaxy brighter than a certain limit, creating a complete three-dimensional map of all the bright galaxies in that region of space. The goal was to see how galaxies were distributed in depth, not just across the sky, but through space. As the months passed and the data accumulated, something remarkable began to emerge. The galaxies weren't scattered uniformly through space as expected. They were arranged in patterns, structures, concentrations that seemed to have some underlying organization. But the patterns weren't fully clear yet. The map wasn't complete enough to see the full picture. The astronomers continued their observations through the late 1970s and into the 1980s. More and more galaxies were added to the map. The structures became more apparent, and gradually a picture emerged that would shock the astronomical community and change our understanding of the universe forever. By the mid-1980s, with several thousand galaxies plotted in three-dimensional space, the structure was undeniable. The galaxies weren't scattered randomly. They were arranged in thin sheets and long filaments, like walls stretching across space. And between these walls were vast empty regions, bubbles of space containing almost no galaxies at all. The team published preliminary results, and the response from other astronomers was a mixture of excitement and skepticism. Could this really be true? Could the universe really have this kind of structure? Some scientists suggested it might be an artifact of the survey design, or a statistical fluke. Others immediately recognized that something profound had been discovered. To settle the question, the survey needed to be extended and completed. More galaxies needed to be observed. The structures needed to be mapped in greater detail, and the results needed to be confirmed by independent surveys observing different regions of the sky. Through the late 1980s, The CFA team continued their work, extending their survey to fainter galaxies and broader regions of sky. And the more they observed, the more dramatic the structures became. In 1989, they published their most comprehensive map yet, and it was stunning. The map showed something that came to be called the Great Wall, though it was nothing like any wall humans have ever built. This was a vast sheet of galaxies extending across hundreds of millions of light years of space, containing thousands of galaxies arranged in a thin layer. The Great Wall stretched from one side of the survey region to the other, so large that its full extent couldn't be determined from the available data. It might extend even farther beyond the boundaries of the survey. And this wasn't the only structure. There were other walls, other filaments, creating a complex network. The galaxies were concentrated along these structures like cities along highways, with vast empty spaces between the highways containing almost nothing. The voids, the empty regions, were equally dramatic. One void in particular, located in the constellation Boötes, was enormous, spanning hundreds of millions of light years with almost no galaxies inside it. This Boötes void had actually been discovered a few years earlier in 1981, but seeing it in the context of the full survey made its significance clear. The voids weren't random empty spaces. They were an integral part of the cosmic structure, bubbles carved out between the filaments and walls where galaxies were concentrated. The scientific community was stunned. This wasn't what anyone had expected. The universe, on its largest scales, had structure, profound, dramatic structure, not just clusters of galaxies, but a grand architecture organizing everything, determining where galaxies formed and where they didn't, creating patterns that extended throughout space as far as anyone could see. Other survey teams quickly confirmed the results. In the early 1990s, another major redshift survey, called the Las Campanas Redshift Survey, mapped galaxies in the southern hemisphere. This survey observed a completely different region of the sky, using different telescopes and different observing strategies. But the results were the same. Galaxies arranged in filaments and walls surrounding empty voids. The cosmic structure wasn't unique to one region. It was everywhere. The question now was, what should this structure be called? It needed a name that captured its essence, its appearance, its nature. The term that caught on was the cosmic web, because that's what it looked like. A vast three-dimensional web stretched across the universe, with galaxies strung along its strands like morning dew on a spider's web, and enormous empty spaces between the strands where almost nothing existed. Let's pause here and really understand what the cosmic web is. Picture in your mind a spider's web, the kind you might see on a dewy morning in a garden. The web has structure. It has radial strands extending outward from the center and spiral strands connecting them, creating a network. Water droplets cling to these strands, making them visible and beautiful, catching the morning light. Between the strands is mostly empty space, just air, but the strands define boundaries and create compartments. Now imagine scaling that web up, not to the size of a room or a building, but to cosmic scales. Imagine a web where each strand is hundreds of millions of light years long, where the droplets clinging to the strands are galaxies, each one containing hundreds of billions of stars, where the empty spaces between the strands are voids, vast bubbles of emptiness, larger than entire superclusters of galaxies. This is the cosmic web, not a flat two-dimensional web, but a three-dimensional network extending in all directions through space, a structure so vast that light takes billions of years to travel from one side to another, a pattern that seems to organize everything in the universe on the largest observable scales. The cosmic web has several distinct components, different types of structures that work together to create the overall pattern. Understanding these components is crucial to appreciating just how remarkable this structure is and how it shapes everything in the universe. First, and perhaps most importantly, are the filaments. These are the strands of the cosmic web, long chains of galaxies stretching across hundreds of millions of light years of space. Filaments are not solid objects, of course. They're more like highways through space, regions where galaxies are concentrated, where matter has accumulated over billions of years. Imagine a string of Christmas lights stretching across a dark room. The string itself is invisible in the darkness, but you can see the lights, and their arrangement reveals the path of the string. Filaments are similar, except the lights are galaxies, and the string stretches not across a room, but across distances so vast that light takes hundreds of millions of years to travel from one end to the other. Filaments vary tremendously in size, shape, and density. Some are relatively narrow, containing just a modest concentration of galaxies, strung out in a thin line through space. Others are thick and massive, containing huge numbers of galaxies packed relatively close together, creating highways of light visible in deep sky surveys. The scale of these filaments is difficult to comprehend. Let me try to give you a sense of just how enormous they are by building up from more familiar distances. Our Milky Way galaxy, our cosmic home, is about 100,000 light years across. That's already an incomprehensibly large distance. Light, traveling at its maximum speed of about 186,000 miles per second, takes 100,000 years to cross our galaxy from edge to edge. The nearest large galaxy to us, Andromeda, sits about 2.5 million light years away. That's 25 times the diameter of the Milky Way, a gulf of space so vast that the light we see from Andromeda tonight left that galaxy 2.5 million years ago, when our ancestors were primitive humans in Africa, just learning to use stone tools. Our local group, the small cluster of galaxies including the Milky Way and Andromeda and several dozen smaller companions, extends about 10 million light years across. That's 100 times the diameter of our galaxy, 4 times the distance to Andromeda. This is the cosmic neighborhood in which we live. But a typical filament dwarfs even this. A modest-sized filament might extend for 200 or 300 million light years, 20 or 30 times larger than our entire local group. Light traveling at its maximum possible speed takes 200 million years to traverse such a filament from end to end. 200 million years ago, dinosaurs were just beginning to dominate Earth. The continents were arranged differently. Life was completely different. And light leaving one end of such a filament back then is only now reaching the other end. The largest filaments are even more immense. Some extend for more than 1 billion light years, distances so vast that light takes longer than 1 billion years to cross them. 1 billion years ago, Earth was a very different planet. Life consisted primarily of simple single-celled organisms. There were no plants, no animals, no complex life of any kind. And light leaving the far end of these giant filaments back then is only now arriving at the near end. These filaments aren't straight lines, by the way. They curve and twist and branch like the limbs of a tree or the arteries and veins in your circulatory system. Sometimes multiple filaments merge together, joining to create even larger structures. Sometimes they branch apart, spreading out across space in different directions. The overall pattern is complex and organic-looking, more like something grown than something built, more like a biological structure than a human-engineered one. And these filaments contain enormous quantities of galaxies. A major filament might contain thousands upon thousands of galaxies strung along its length like beads on an incredibly long string. Each galaxy contains hundreds of billions of stars. Each star is a sun, possibly with planets orbiting it. The amount of matter in a single large filament is staggering, equivalent to perhaps quadrillions of times the mass of our sun, a significant fraction of all the ordinary matter in the observable universe concentrated into these cosmic highways. Let me tell you about some of the most remarkable filaments that have been discovered, so you can appreciate the true scale and grandeur of these structures. One of the most famous is the Sloan Great Wall, discovered in 2003 by astronomers analyzing data from the Sloan Digital Sky Survey, one of the most ambitious astronomical surveys ever undertaken. The Sloan Great Wall is a colossal structure extending for about 1.37 billion light years, making it one of the largest known structures in the entire universe. It contains thousands of galaxies, including several massive galaxy clusters, all connected together into one enormous filament stretching across a significant fraction of the observable universe. When this structure was first discovered, astronomers were shocked by its size. Even though they knew the cosmic web existed, even though they'd been mapping filaments for 2 decades, this structure was larger than anything they'd seen before. It challenged their understanding of how such massive structures could form and remain coherent over billions of years. Even more remarkable is the Hercules Corona Borealis Great Wall, discovered in 2013. This structure is almost incomprehensibly vast, extending for roughly 10 billion light years, though its exact boundaries are difficult to define and measure precisely. If this structure is real and as large as measurements suggest, it approaches the scale of the observable universe itself. It may be the largest single structure that could possibly exist in our universe. The discovery of the Hercules Corona Borealis Great Wall was controversial precisely because of its size. Some astronomers question whether something this large can really be considered a single coherent structure, or whether it's just a statistical alignment of several separate structures that happen to appear connected from our vantage point. The debate continues, but even the possibility that such a structure exists tells us something profound about the universe and the scales on which structure can form. There are many other named filaments scattered throughout the catalogs of astronomers. The Pisces Cetus Supercluster complex stretches for 1 billion light years. The Boss Great Wall extends for similar distances. Each new deep survey of the universe reveals more filaments, more structure, more evidence that the cosmic web extends everywhere we look. These filaments are not static, frozen structures. They're dynamic, evolving over billions of years. Galaxies within filaments are moving, flowing along the filaments like traffic on a highway. They're pulled by gravity toward the densest regions, toward the nodes where multiple filaments intersect. Over time, the filaments grow denser as more matter flows into them. Some filaments merge with others, creating larger structures. The cosmic web is alive in a sense, constantly changing and evolving, though on timescales so vast that we can't directly observe the changes. Now let's turn our attention to the second major component of the cosmic web, the voids. If filaments are where galaxies are found, voids are where they're conspicuously absent. These are the empty regions, the bubbles of space carved out between the filaments, regions that contain far fewer galaxies than average. Voids are absolutely enormous, often larger than even the longest filaments. A typical void might span 300 to 500 million light-years across, creating a bubble of near emptiness, larger than entire superclusters of galaxies. The largest voids extend for more than 1 billion light-years, vast cavities in the cosmic structure that contain almost nothing. And when astronomers say these regions are empty, they really mean it. A typical void contains only about 10% of the number of galaxies you'd expect to find in a similar volume of space elsewhere. Some voids are even emptier, containing less than 1% of the expected number of galaxies. It's as if matter has been scooped out of these regions, leaving behind vast bubbles of near emptiness. Imagine a sphere 1 billion light-years in diameter. If galaxies were distributed uniformly through space at the average density of the universe, such a sphere should contain hundreds of thousands or even millions of galaxies, depending on exactly where you set your cutoffs for what counts as a galaxy. But in a void of this size, you might find only a few thousand galaxies, or in extreme cases, only a few hundred scattered through the vast volume. The galaxies that do exist within voids are often strange and unusual compared to galaxies in denser regions. They tend to be small dwarf galaxies rather than large spirals or ellipticals. They tend to be dim, containing fewer stars and producing less light than typical galaxies. And they're usually isolated, drifting alone through the emptiness with no nearby companions, no galaxy clusters, no rich groups. These void galaxies probably formed differently than galaxies in filaments and clusters. In dense regions, galaxies interact frequently. They collide and merge, stripping gas from each other, triggering bursts of star formation through gravitational interactions. This creates large, bright galaxies with complex structures and active star formation. But void galaxies form in isolation, growing slowly and peacefully over billions of years. They accumulate matter gradually from their surroundings, forming stars at modest rates without the dramatic events that shape galaxies and denser environments. The result is a population of small, dim, lonely galaxies drifting through the cosmic emptiness. One of the most famous voids is the Bootes void, also sometimes called the Great Nothing. Discovered in 1981 by astronomers Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman, this void is roughly 330 million light-years in diameter and contains only about 60 galaxies, where it should contain thousands if galaxies were distributed uniformly. When the Bootes void was first discovered, some astronomers wondered if it might be a mistake, an artifact of incomplete observations or systematic errors in distance measurements. But further observations confirmed it was real. There really is a vast bubble of near emptiness in the direction of the constellation Bootes, a region of space where galaxies are extraordinarily rare. The existence of voids like this raises profound questions. How did they form? Why are they so empty? What happened to all the matter that should be there? The answers lie in understanding how cosmic structure formed in the first place, a topic we'll explore more deeply in the next part of our journey. But the basic answer is that voids are regions that started slightly less dense than average in the early universe, and over billions of years, gravity pulled matter out of these regions toward denser areas nearby, evacuating the voids and concentrating matter in filaments. Closer to home is something called the local void, a relatively modest void by cosmic standards, only about 150 million light-years across. We're not inside this void, thankfully, but we're near its edge, on the boundary between the void and the filament. The local void influences our cosmic neighborhood, affecting how galaxies around us move and interact. In fact, recent studies have shown that we're being pushed away from the local void by what astronomers call the Dipole Repeller effect. The void doesn't actively push us, of course. Rather, its lack of gravitational pull allows gravity from denser regions on the opposite side of us to dominate, effectively causing the local void to repel us. We'll talk more about this fascinating phenomenon shortly when we discuss our motion through the cosmic web. Voids aren't completely empty, of course. They contain some matter, just far less than average regions. There's gas floating through the voids, thin wisps of hydrogen and helium spread incredibly thinly through space. There are probably dark matter particles passing through as well, though in lower densities than elsewhere. And there are those few scattered galaxies, lonely islands of light in the darkness. Some voids also contain faint filamentary structures within them, thin threads of slightly enhanced density connecting the few galaxies that exist inside. These are like the veins within a leaf, much smaller and fainter than the main cosmic web filaments, but following similar patterns. Even within the emptiest regions, matter organizes itself into structures on smaller scales. The voids are as fundamental to the cosmic web as the filaments. They're not just empty spaces between more interesting structures. They're an essential component of the pattern, the negative space that defines the shape of the positive structures. Without voids, there would be no filaments, no walls, no dramatic contrast in density. The voids and filaments are two sides of the same coin, both produced by the same process of gravitational structure formation. The third major component of the cosmic web consists of the nodes, the places where multiple filaments intersect, the junction points in the cosmic network where several highways come together. And at these intersections you find the densest concentrations of galaxies in the entire universe, the galaxy clusters. A galaxy cluster is an immense collection of galaxies bound together by gravity. Where the Milky Way is one galaxy in a small group of about 50, a major cluster can contain thousands of galaxies packed into a relatively compact volume of space. The gravitational binding is so strong that these galaxies orbit around each other, held together as a single gravitationally bound system, despite the enormous distances between individual galaxies. The nearest large cluster to us is the Virgo cluster, which we've mentioned before. Located about 50 to 60 million light-years away in the direction of the constellation Virgo, this cluster contains over 1,300 large galaxies and thousands more smaller dwarf galaxies. The cluster extends across about 15 million light-years of space, with galaxies orbiting around the cluster's center of mass. At the heart of the Virgo cluster sits a giant elliptical galaxy called M87, a monster galaxy containing several trillion stars. This galaxy is so massive that it dominates the gravitational field of the entire cluster. Many of the other galaxies in the cluster are slowly falling toward M87, and over billions of years, some of them will merge with it, making it even larger. The Virgo cluster is the gravitational anchor of our local cosmic region. Our local group of galaxies, including the Milky Way, is actually falling toward the Virgo cluster, pulled by its enormous gravitational field. We're moving toward Virgo at about 200 to 300 miles per second, though we'll never actually reach it because the expansion of the universe is carrying distant objects away faster than we can fall toward them. Even larger than the Virgo cluster is the Coma cluster, located about 300 million light-years away. This massive cluster contains over 1,000 large galaxies and thousands of smaller ones, all packed into a region only about 20 million light-years across. The galaxies in the Coma cluster are moving at tremendous speeds, sometimes more than 1,000 miles per second, held in their orbits by the cluster's immense gravitational field. Fritz Zwicky's study of the Coma cluster, which we discussed earlier, revealed that most of the cluster's mass is dark matter, invisible material that doesn't emit or absorb light. The visible galaxies account for only a small fraction of the total mass. Even the hot gas between the galaxies, which contains more mass than all the stars combined, is still just a minor component. Dark matter dominates, forming an enormous invisible halo that binds the cluster together. This pattern holds for all galaxy clusters. They're held together primarily by dark matter, with visible galaxies and hot gas as minor components. The dark matter formed first, creating gravitational wells that attracted ordinary matter. Over time, galaxies fell into these dark matter halos and accumulated in clusters. The dark matter is the scaffold, the invisible structure on which the visible universe is built. The space between galaxies in a cluster isn't empty. It's filled with extremely hot gas, heated to millions of degrees by the gravitational energy of the cluster. As gas falls into the cluster, it accelerates, converting gravitational potential energy into kinetic energy into motion. And when gas particles moving at high speeds collide with each other, that kinetic energy converts into heat, raising the temperature of the gas to millions of degrees. Gas this hot glows with X-rays, high-energy photons that can be detected by X-ray telescopes in space. In fact, galaxy clusters are among the brightest X-ray sources in the universe. The hot gas extends throughout the cluster volume, far beyond the visible galaxies, filling the space between them with an ultra-hot plasma that would vaporize any planet instantly if it somehow wandered into the cluster core. These galaxy clusters mark the nodes of the cosmic web, the places where multiple filaments intersect. Galaxies flowing along filaments are funneled toward these intersection points, accumulating in ever larger numbers. Over billions of years, more and more galaxies arrive, and the cluster grows more massive, its gravitational pull strengthening, attracting even more galaxies. It's a self-reinforcing process that creates the densest concentrations of matter in the universe. Some clusters are isolated, connected to the cosmic web by only one or two filaments. Others are major hubs connected to 4 or 5 or even more filaments, making them central junctions in the network. These major clusters play crucial roles in defining the large-scale structure, organizing the flow of matter throughout their cosmic neighborhoods. So we have filaments, voids, and nodes, 3 distinct components working together to create the cosmic web. Filaments are highways of galaxies stretching across hundreds of millions of light years. Voids are vast empty bubbles between the highways. Nodes are intersection points where highways meet, creating dense clusters of thousands of galaxies. And this structure, this cosmic web, extends throughout the observable universe as far as we can see. Every deep survey reveals the same pattern: filaments, voids, and clusters arranged in a complex three-dimensional network. The cosmic web is not a local phenomenon, not something unique to our cosmic neighborhood. It's a fundamental feature of the universe's architecture on the largest observable scales. And here's something remarkable that we need to talk about. You're inside this structure right now. The Milky Way galaxy is part of the cosmic web. You're not an outside observer looking at the structure from a distance. You're embedded in it, surrounded by it, moving through it. Let me give you our complete cosmic address, our exact location within this vast hidden structure. Start with Earth, our home planet, a rocky world about 8,000 miles in diameter, orbiting the Sun at a distance of 93 million miles, completing one orbit every year. Earth is in the solar system, a collection of planets, moons, asteroids, and comets all orbiting the Sun, our nearest star. The solar system extends out to the Oort cloud, perhaps 2 light years from the Sun, marking the boundary of the Sun's gravitational influence. The solar system is located in the Milky Way galaxy, about 26,000 light years from the galactic center. We're in what's called the Orion Arm or Orion Spur, a minor spiral arm between 2 major arms. We orbit the galactic center at about 500,000 miles per hour, taking about 230 million years to complete one orbit. The Milky Way is part of the local group, a small cluster of about 50 galaxies spread across roughly 10 million light years. The local group includes Andromeda, the Triangulum galaxy, and several dozen smaller dwarf galaxies. This is our immediate cosmic neighborhood, the galaxies close enough that we could potentially observe them in great detail, or, in the far future, even visit them if we developed technology for intergalactic travel. The local group is part of the Virgo Supercluster, a much larger structure containing dozens of galaxy groups and clusters spread across about 110 million light-years. The massive Virgo cluster sits near the center of this supercluster, while we're in the outer regions relatively far from the center. But even the Virgo supercluster isn't the full picture. Recent observations have revealed that our supercluster is part of an even larger structure called Laniakea, a Hawaiian name meaning immense heaven. Laniakea extends about 520 million light-years across and contains about 100,000 galaxies, including our Milky Way, the Virgo cluster, and numerous other galaxy groups and clusters. Laniakea was discovered by studying the motions of galaxies. By mapping how galaxies are moving, astronomers can trace the flow of matter through space, identifying the gravitational basins that galaxies are falling into. Laniakea is one such basin, a region where galaxies are all flowing toward a common center, bound together by gravity, despite the expansion of the universe. And Laniakea itself is part of a filament, a strand of the cosmic web connecting to other filaments that extend across hundreds of millions or billions of light years. This filament is part of the larger cosmic web that fills the observable universe, connecting everything together into one vast network. So here's our complete cosmic address: Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea, Cosmic Web Filament, Observable Universe. We're nested inside structure upon structure upon structure, each level larger than the last, each one part of the grand architecture, organizing everything on the largest scales. And we're not sitting still in this structure. We're moving, flowing through the cosmic web along with billions of other galaxies, pulled by massive structures ahead of us and pushed by empty voids behind us. Our solar system orbits the center of the Milky Way at about 500,000 miles per hour, as we mentioned. But the Milky Way itself is also moving. It's being pulled by gravity toward the Andromeda Galaxy, and the two will collide and merge in about 4 billion years. This isn't a problem for us, by the way. The stars are so far apart that they'll mostly pass by each other without colliding. But the two galaxies will merge over hundreds of millions of years, their shapes distorted by tidal forces, eventually settling into a single large elliptical galaxy. But beyond this local motion, our entire local group is being pulled through space by larger gravitational influences. There's something called the Great Attractor, a gravitational anomaly located about 200 million light-years away in the direction of the constellations Hydra and Centaurus. This region contains several massive galaxy clusters, including the Norma cluster, whose combined mass creates a powerful gravitational pull on our local group and on thousands of other galaxies around us. We are falling toward the Great Attractor at about 400 miles per second, pulled by its gravity along with countless other galaxies. This motion is in addition to our motion around the Milky Way's center and our motion toward Andromeda. We're moving in multiple directions simultaneously, our trajectory determined by the combined gravitational pull of all the matter around us. But that's not the whole story. We're not just being pulled toward the Great Attractor. We're also being pushed away from something on the opposite side of the sky. This pushing comes from what astronomers call the Dipole Repeller, a large underdense region, essentially an enormous void, located opposite the Great Attractor from our perspective. The Dipole Repeller doesn't actively push us, of course. Empty regions don't generate repulsive forces. Rather, the void's lack of mass means it contributes very little gravitational pull on us. Meanwhile, the Great Attractor on the opposite side pulls strongly. The combined effect is that we're being pulled away from the void and toward the Great Attractor, making it seem as though the void is repelling us. This dipole structure with a massive attractor on one side and a large void on the other helps explain our motion through the cosmic web. We're flowing along a filament, pulled toward denser regions ahead and pushed by empty regions behind, part of a vast cosmic flow involving hundreds of thousands of galaxies all moving together through the hidden structure of the universe. Mapping these motions has revealed the shape of Laniakea and showed us where we fit in the cosmic web. By tracing the flow of galaxies, astronomers can identify the boundaries between different superclusters, the watershed lines where the flow changes direction. Just as water flowing down a mountain follows the contours of the land, with different streams flowing into different valleys, galaxies flow through the cosmic web, along paths determined by the distribution of matter. Laniakea is one drainage basin in this cosmic landscape. All the galaxies within Laniakea are flowing toward a common center, a region of particularly high density where multiple filaments intersect. Beyond the boundaries of Laniakea are other superclusters, other basins where galaxies flow toward different centers. The cosmic web organizes these flows, channeling matter along filaments, concentrating it at nodes, evacuating it from voids. And yet, despite living inside this structure, despite being surrounded by it and moving through it every moment, most people have never heard of the cosmic web. Why not? Why is this remarkable structure, this grand architecture, organizing everything on the largest scales, so unknown? The answer comes down to scale, perspective, and the limitations of human perception. First, there's the problem of scale. The cosmic web is simply too large to see from our vantage point inside it. It's like being a fish in the ocean, trying to understand the ocean itself. The fish is surrounded by water, moves through it constantly, depends on it for survival. But the ocean is too large, too pervasive, too all-encompassing for the fish to perceive it as a distinct structure. The ocean is simply the environment, the medium, the background against which everything else happens. We're in a similar situation with the cosmic web. We're swimming through it, embedded in one of its filaments, surrounded by its structures. But we can't step outside and view it from a distance. We can't get the perspective needed to see the full pattern. We're too close, too immersed, too much a part of the structure to see it clearly from our inside perspective. Second, there's the problem of time and distance. The cosmic web extends across such vast distances that light takes hundreds of millions of years to cross from one feature to another. When we look at distant galaxies, we're seeing them as they were long ago, not as they are now. We're looking backward in time, and the farther we look, the farther back we see. This makes it incredibly difficult to perceive structure directly. We're not seeing the cosmic web as it exists now, all at once. We're seeing different parts of it at different times in the past, like trying to understand the layout of a city when you can only see each neighborhood at a different point in history, some as they looked yesterday, others last year, others a century ago. To discover the cosmic web, astronomers had to painstakingly map the positions of thousands upon thousands of galaxies, measure their distances using redshift, plot them in three-dimensional space, and look for patterns. They had to correct for the expansion of the universe, account for our own motion through space, and use sophisticated statistical techniques to separate real structure from random fluctuations. They also had to build computer simulations of how structure forms in the universe, running virtual universes forward from the Big Bang to the present day, letting gravity and dark matter and cosmic expansion work together to create structure. These simulations could then be compared to observations to verify that scientists understood the process correctly. Only through decades of this careful work did the hidden structure finally reveal itself. The cosmic web was there all along, organizing everything, but it took immense effort and technological advancement to discover it and map it and understand it. And even now, even with this understanding, the cosmic web remains largely unknown to the general public. It's a relatively recent discovery in the grand scheme of things, only fully appreciated in the last few decades. Most people learn about stars and planets and galaxies in school, but few learn about the cosmic web, about how galaxies are organized on the largest scales, about the filaments and voids that structure the universe. But you know now, you've learned one of the universe's deepest secrets tonight. You understand that the cosmos isn't random but structured, that there's a hidden architecture organizing everything on the largest scales, and that you're part of this structure, embedded in it, moving through it, shaped by it over billions of years of cosmic history. The universe has revealed something profound to you, and there's more to discover, more questions to answer about how this structure formed, where it came from, and where it's going in the distant future. Those questions await us in the next part of our journey. But for now, rest here with this knowledge. The cosmic web surrounds you. You're inside it, part of it, connected through billions of years of cosmic evolution to structures stretching across billions of light years of space. You're small, yes, but you're also part of something vast and grand and beautiful, something that gives shape and meaning to the universe itself. So here we are, having discovered the cosmic web, the hidden structure of the universe. We've seen how galaxies are arranged in filaments and walls surrounding vast empty voids. We've learned about the nodes where filaments intersect, creating massive clusters containing thousands of galaxies. And we've understood our own location within this structure, embedded in a filament, part of the grand architecture that organizes everything on the largest scales. But knowing the cosmic web exists raises even deeper questions. Where did this structure come from? How did it form? The universe began in the Big Bang about 13.8 billion years ago, hot and dense and remarkably uniform. So how did we get from that smooth beginning to the complex web of structure we see today? What forces shaped the cosmic web into its current configuration? The story of how cosmic structure formed is one of the most beautiful narratives in all of science. It involves gravity, dark matter, the expansion of the universe, and billions of years of evolution. And understanding this story helps us appreciate not just where the cosmic web came from, but where it's going, how it will change in the future, and what all of this means for our place in the cosmos. Let's go back to the beginning, back to the Big Bang, back to a time when the universe was incredibly hot, incredibly dense, and filled with a nearly uniform soup of energy and matter. In the first moments after the Big Bang, the universe was so hot that atoms couldn't exist. Matter existed as a plasma, a sea of free electrons and atomic nuclei mixed together, constantly colliding and scattering light. The universe was opaque, like being inside a thick fog, because light couldn't travel far without hitting a particle and being scattered in a new direction. As the universe expanded, it cooled. After about 380,000 years, it had cooled enough for electrons and nuclei to combine into neutral atoms, primarily hydrogen and helium. Once this happened, light could suddenly travel freely through space. The universe became transparent for the first time. This moment is called recombination, and the light that was released at this moment is still traveling through the universe today as the cosmic microwave background radiation, the afterglow of the Big Bang. Now here's the crucial thing. When we observe this cosmic microwave background radiation today, using sensitive detectors on satellites like the Planck spacecraft, we can map the temperature of this ancient light across the entire sky. And what we find is that the temperature is remarkably uniform, the same in every direction to within about 1 part in 100,000, but not perfectly uniform. There are tiny variations, tiny fluctuations in temperature from one region of the sky to another. These fluctuations are incredibly small, differences of only about 30 millionths of a degree. But they're real, and they're profoundly important because they represent density variations in the early universe. Regions where the cosmic microwave background is slightly hotter were slightly denser than average. Regions where it's slightly cooler were slightly less dense than average. These tiny density variations imprinted in the universe when it was only 380,000 years old were the seeds from which all cosmic structure would eventually grow. But why were there density variations in the first place? If the Big Bang started from a perfectly uniform state, how did these fluctuations arise? The answer, according to our best current understanding, lies in quantum mechanics and something called inflation. In the very first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion called inflation. During this brief moment, the universe expanded by an enormous factor, growing from subatomic size to perhaps as large as a grapefruit or basketball in an unimaginably short time. This inflationary expansion was driven by a special form of energy that filled space, and it solved several problems in cosmology. But for our purposes, the important thing is that inflation stretched quantum fluctuations, tiny random variations that exist at the smallest scales in quantum mechanics, up to cosmic size. These quantum fluctuations became the density variations we see in the cosmic microwave background. Regions that were slightly denser than average by quantum chance got stretched to enormous size by inflation, creating the initial seeds for cosmic structure. It's a remarkable idea. The largest structures in the universe, filaments stretching across billions of light years, originated as quantum fluctuations smaller than an atom, blown up to cosmic proportions by the inflationary expansion of space itself. Once these density variations existed, gravity could begin to amplify them, and this is where the story of structure formation really begins. Gravity is an attractive force. Any region that's slightly denser than average has slightly stronger gravity, pulling on the matter around it. This extra gravity attracts more matter, making the region denser still. As it gets denser, its gravity strengthens further, attracting even more matter. It's a runaway process, a feedback loop where density attracts matter, which increases density, which strengthens gravity, which attracts more matter. Meanwhile, regions that are slightly less dense than average have slightly weaker gravity. They can't hold on to their matter as well. Matter flows out of these underdense regions toward denser regions nearby. As matter leaves, the regions become even less dense. Their gravity weakens further, and more matter flows out. These underdense regions become the voids. This process is called gravitational instability, and it's the fundamental mechanism by which cosmic structure forms. Small variations in density grow over time, amplified by gravity until they become large variations, dramatic differences between dense filaments and empty voids. But there's a complication. In the early universe, for the first few 100,000 years, ordinary matter couldn't clump together efficiently. The universe was filled with radiation, intense light left over from the Big Bang, and this radiation pressure prevented matter from collapsing under its own gravity. The matter wanted to clump, but the radiation kept pushing it apart, preventing structure from forming. This is where dark matter becomes crucial to the story. Dark matter doesn't interact with light. It doesn't feel radiation pressure, so dark matter could begin clumping together immediately after the Big Bang, unimpeded by the intense radiation filling the early universe. Dark matter consists of particles that don't emit, absorb, or scatter light. We don't know exactly what these particles are. They're not atoms or any form of ordinary matter. There's something else entirely, something that makes its presence known only through gravitational effects. But whatever they are, they're abundant, making up about 85% of all matter in the universe. Because dark matter could clump freely in the early universe while ordinary matter could not, dark matter formed a skeleton of cosmic structure. It collapsed into filaments and walls and nodes, creating gravitational wells, regions of enhanced gravity where ordinary matter would eventually accumulate once the universe cooled enough for radiation pressure to become negligible. After recombination, after the universe became transparent and radiation could stream freely through space without constantly scattering off matter, ordinary matter finally became free to fall into the gravitational wells created by dark matter. Hydrogen and helium gas began flowing along dark matter filaments, accumulating in dark matter halos, following the pattern established by the invisible dark matter structure. Over millions and billions of years, this gas accumulated in dense enough concentrations to begin forming stars. The first stars ignited perhaps a few 100 million years after the Big Bang, lighting up the universe for the first time since recombination. These first stars were massive and short-lived, burning through their fuel in just a few million years before exploding as supernovas. These explosions seeded space with heavier elements, carbon and oxygen and iron, and all the other elements created in stellar cores and supernova explosions. Subsequent generations of stars formed from gas enriched with these heavier elements, and around some of these stars, planets formed, rocky worlds and gas giants that inherited the chemical complexity created by earlier generations of stars. Galaxies began to take shape as stars accumulated in gravitational wells. Small galaxies formed first, collections of perhaps millions or billions of stars bound together by their mutual gravity and by the gravity of the dark matter halos surrounding them. These small galaxies then merged with each other, combining to form larger galaxies through countless collisions and mergers over billions of years. And throughout this entire process, the cosmic web structure became more and more pronounced. Matter continued flowing along filaments toward nodes. Voids expanded as matter flowed out of them. Clusters of galaxies grew larger and more massive as more galaxies fell into them. The pattern established by tiny quantum fluctuations in the first fraction of a second after the Big Bang was amplified over billions of years by gravity and dark matter into the cosmic web we observe today. Astronomers can simulate this process using powerful supercomputers. They start with a virtual universe just after the Big Bang, filled with dark matter and ordinary matter distributed according to the tiny density variations observed in the cosmic microwave background. They let gravity act, allowing matter to attract other matter, clump together, form structures. They include the expansion of the universe, stretching space itself and carrying distant matter apart. They track billions of dark matter particles as they flow through space, accumulating in filaments and halos. These simulations run forward in time, from the Big Bang to the present day, showing how structure forms and evolves. And the results are stunning. The simulations produce cosmic webs that look remarkably similar to what we observe in the real universe. Filaments, voids, and nodes arranged in complex three-dimensional networks. The simulations match observations so well that it gives astronomers confidence they understand the basic process of structure formation. One of the most famous of these simulations is called the Millennium Run, conducted in 2005. This simulation tracked more than 10 billion dark matter particles in a cubic region of space over 1 billion light years on a side, following their evolution from shortly after the Big Bang to the present day. The result was a detailed picture of how structure forms, showing dark matter accumulating into filaments and halos, creating the framework on which galaxies would eventually form. More recent simulations like the Sleepless project and the Eagle simulations have added ordinary matter and star formation to these dark matter simulations, creating virtual universes where galaxies form and evolve in realistic ways. These simulations can be compared directly to observations, allowing astronomers to test their understanding of galaxy formation and cosmic structure. The agreement between simulations and observations is remarkable. The cosmic web that emerges from simulations based on simple physical laws, gravity and dark matter, and cosmic expansion matches in detail what we see when we map the real universe. This gives us confidence that we understand, at least in broad strokes, how the universe's hidden structure came to be. But the cosmic web isn't static. It's still evolving, still changing, driven by the same processes that created it in the first place. Gravity continues to pull matter into filaments and clusters. Voids continue to expand as matter flows out of them. The structure is becoming more pronounced over time, with denser regions getting denser and emptier regions getting emptier. And there's another force at play now that will profoundly affect the future evolution of cosmic structure: dark energy. Dark energy is perhaps the most mysterious component of the universe. It's a form of energy that fills all of space, and unlike ordinary matter or dark matter, it doesn't clump or cluster. It's uniformly distributed, the same density everywhere. And it has a remarkable property. It causes the expansion of the universe to accelerate. We've known since the 1920s that the universe is expanding, that galaxies are moving apart as space itself stretches. For most of the 20th century, astronomers assumed this expansion was slowing down over time, decelerated by the gravitational pull of all the matter in the universe trying to pull everything back together. But in the late 1990s, observations of distant supernovas revealed something shocking. The expansion of the universe isn't slowing down, it's speeding up. Somehow, space is expanding faster and faster over time, as if something is pushing everything apart. This something is dark energy, and it makes up about 68% of the total energy density of the universe. Dark matter accounts for about 27%. Ordinary matter, the atoms that make up stars and planets and people, accounts for only about 5%. We live in a universe dominated by dark energy and dark matter, with ordinary matter as a minor component. Dark energy's effect on cosmic structure is profound. As the universe's expansion accelerates, it becomes harder for gravity to pull distant structures together. Regions that are currently separate will likely remain separate forever, unable to overcome the accelerating expansion pushing them apart. This means the cosmic web has a kind of boundary or horizon. Structures within a few 100 million light years of us are gravitationally bound together. They're part of Laniakea, our local region of the cosmic web, and they'll remain connected to us indefinitely. But structures much farther away are receding faster due to the expansion of space, and we'll gradually lose contact with them as they're carried beyond our horizon by the accelerating expansion. In the far future, billions of years from now, galaxies beyond our local region will have been carried so far away by cosmic expansion that their light will no longer reach us. An observer in the distant future will see a much smaller observable universe than we see today, containing only the galaxies in our local supercluster, with everything else having disappeared beyond the cosmic horizon. But within our local region, structure formation will continue. Galaxies will continue merging. The Milky Way and Andromeda will collide and merge in about 4 billion years, forming a large elliptical galaxy, sometimes called Milkomeda or Milkdromeda. Other galaxies in the local group will eventually merge as well, and over tens of billions of years, all the galaxies in our local region might merge into a single giant galaxy. Clusters will also continue to grow. The Virgo cluster will accumulate more galaxies over time, becoming more massive and more tightly bound. Small groups like our local group might eventually fall into nearby clusters, merging with them over billions of years. The voids will continue to expand. As matter flows out of underdense regions toward filaments and clusters, the voids will grow larger and emptier. Eventually, almost all matter will be concentrated in a relatively small number of superclusters and giant galaxies, separated by vast expanses of nearly empty space. But even this isn't the end of the story. On even longer timescales, trillions of years in the future, stars will exhaust their fuel and die. Star formation will gradually cease as the available gas is used up or dispersed. The universe will enter an era where existing stars slowly burn out, one by one, leaving behind dark remnants, white dwarfs, neutron stars, and black holes. After all the stars have died, the cosmic web will still exist in some form, but it will be dark and visible, detectable only through gravitational effects. The filaments will be traced by dark matter and dead stars rather than glowing galaxies. The structure will persist, but it will be a fossil of what once was, a ghost of the luminous cosmic web we observe today. Eventually, even black holes will evaporate through Hawking radiation, a process that takes unimaginably long times, far longer than the current age of the universe. After the black holes are gone, the universe will consist only of fundamental particles scattered through an ever-expanding space, with no structure, no pattern, no organization remaining. The cosmic web will have dissolved completely, erased by the relentless expansion of space and the slow decay of all structure. But that fate is so far in the future that it's barely worth contemplating. For now, for the foreseeable future spanning trillions of years, the cosmic web will remain, a beautiful and profound structure organizing the universe on the largest scales. Let's return to the present and think more deeply about what all of this means. We've learned that the universe has hidden structure, that galaxies are organized into a cosmic web of filaments, voids, and nodes. We've seen how this structure formed through gravity and dark matter over billions of years, and we've understood our place within this structure. But what does this tell us about the universe more broadly? What insights can we gain from knowing about the cosmic web? First, the cosmic web tells us that the universe is comprehensible. It follows laws, patterns, rules that we can discover and understand. The same physics that governs falling objects on Earth also governs the formation of structure spanning billions of light years. Gravity works the same way everywhere. Dark matter, though mysterious in its nature, behaves in predictable ways that we can model and simulate. The universe makes sense, at least in its broad outlines, and we can figure it out through observation, experimentation, and theoretical reasoning. Second, the cosmic web reveals deep connections between the very large and the very small. The largest structures in the universe originated as quantum fluctuations, tiny variations at the smallest possible scales. These microscopic fluctuations were inflated to cosmic size and then amplified by gravity over billions of years to create filaments stretching across billions of light years. There's a profound connection between quantum mechanics, which governs the subatomic world, and cosmology, which studies the universe as a whole. They're not separate domains, but intimately linked aspects of a unified physical reality. Third, the cosmic web shows us that the universe has a history, a narrative, a story of evolution from simple beginnings to complex present. The universe started hot, dense, and nearly uniform. Over billions of years, it cooled, expanded, and developed structure through natural processes. This is a story of increasing complexity emerging from simplicity, order arising from chaos, structure forming from an initially smooth beginning. It's a story we can trace and understand, connecting the early universe to the cosmos we observe today. Fourth, and perhaps most importantly, the cosmic web reminds us of our place in the larger scheme of things. We're part of something vast and ancient and beautiful. We're embedded in a structure that extends across billions of light years and has been evolving for billions of years. The atoms in our bodies were formed in stars that formed in galaxies that formed along the filaments of the cosmic web, shaped by processes playing out over cosmic scales and cosmic timescales. This perspective can be humbling. We're so small compared to the cosmic web. Our entire planet is a speck in our galaxy, and our galaxy is just one among billions arranged in vast structures we can barely comprehend. Our lives are brief flickers of consciousness in the vast sweep of cosmic time. Everything we worry about, everything that seems important in our daily lives, is infinitesimally small in cosmic context. But this perspective can also be empowering and comforting. We're part of something larger than ourselves. We're connected through billions of years of cosmic history to structures stretching across the observable universe. We're made of star stuff, as Carl Sagan famously said, atoms forged in stellar cores and distributed by supernova explosions along cosmic web filaments until they eventually became part of planets and people. And we're the part of the universe that's become conscious, that can look back at itself and understand what it is and where it came from. The cosmic web, through some remarkable process we don't fully understand, has organized matter in such a way that consciousness has emerged. In us, in humans, and perhaps in other forms of life scattered among the trillions of planets throughout the cosmic web, the universe has become aware of itself. This is remarkable when you think about it. For billions of years after the Big Bang, the universe existed but had no awareness of its own existence. Galaxies formed and evolved, stars ignited and died, planets orbited their suns, all without any consciousness to observe or appreciate it. But eventually, on at least one small rocky planet, orbiting an ordinary star in an unremarkable galaxy, life emerged and evolved and eventually produced beings capable of thought, of wonder, of asking questions about the cosmos. We're those beings. We're the universe's way of knowing itself, understanding itself, marveling at its own complexity and beauty. Every time you look up at the night sky and feel awe at the stars, every time you read about cosmic discoveries and feel a sense of wonder, you're participating in something profound. You're the cosmos examining itself, appreciating itself, trying to understand its own nature. The fact that we exist, that we can think and wonder and understand, that we can discover the cosmic web and trace its formation back to the Big Bang and forward to the distant future, this is itself a kind of miracle. Not a supernatural miracle, but a natural one, an extraordinary consequence of natural laws playing out over billions of years on cosmic scales. And this brings us to another profound question. Are we alone in experiencing this awareness? Are we the only conscious beings in the cosmic web, or are there others scattered among the stars? We don't know the answer. We've found no evidence of life beyond Earth despite decades of searching. We've detected no signals from alien civilizations, no obvious signs of intelligence in the cosmos. The universe appears silent, empty of other voices. But the cosmic web contains trillions of galaxies, and each galaxy contains hundreds of billions of stars, and many of those stars have planets. The sheer number of possible locations for life is staggering. It seems unlikely that Earth is the only place where life emerged, the only planet where evolution produced intelligent, technological beings capable of contemplating the cosmos. Perhaps life is common, but intelligence is rare, with most life remaining simple and microbial, never developing the complexity needed for consciousness and technology. Perhaps intelligent civilizations arise frequently but destroy themselves quickly, succumbing to war or environmental catastrophe or some other disaster before they can leave lasting marks on the cosmos. Or perhaps the distances between stars and galaxies are simply too vast for civilizations to ever make contact. Even if the cosmic web contains millions of intelligent species, they might all be isolated, separated by hundreds or thousands of light years, unable to communicate or travel between stars, each one wondering if they're alone, never finding the answer. Or perhaps we truly are alone, the only consciousness in a vast unconscious universe. Perhaps life requires such an unlikely combination of conditions that it's extraordinarily rare, and consciousness even rarer. Perhaps we're a cosmic accident, a statistical fluke, the one place in trillions of worlds where everything aligned just right to produce awareness. Either answer is profound. If we're not alone, if the cosmic web contains countless other civilizations, then we're part of a vast cosmic community, and perhaps someday we'll make contact and learn we're not unique. If we are alone, if consciousness is rare or unique to Earth, then we have a special responsibility to preserve and cherish it, to recognize that awareness is a precious and fragile thing that deserves protection. We may never know which answer is correct. The distances involved are so vast, the timescales so long that we might never detect other civilizations even if they exist. But the question itself, the wondering, the searching, this is part of what makes us human, part of what makes consciousness valuable. Let's think now about scale and perspective, because one of the most valuable things the cosmic web teaches us is how to think about size and significance. In your daily life, you operate at human scales, rooms and buildings and streets and cities, distances measured in feet or miles, times measured in minutes or hours or days. These are the scales that feel real and immediate and important. A traffic jam is frustrating. A missed appointment matters. Interpersonal conflicts feel significant. These concerns occupy your mind because they're happening at scales you can directly perceive and interact with. But zoom out to cosmic scales, and these concerns become invisible. From the perspective of the cosmic web, your entire planet is a point, your galaxy is one among billions. Your entire lifespan is less than a microsecond of cosmic time. The traffic jam that frustrated you this morning doesn't even register on cosmic scales. The argument you had last week, the deadline you're worried about, the 1,000 small concerns that occupy your daily thoughts, all of them are utterly insignificant in the grand cosmic scheme. This perspective can be liberating. When you feel overwhelmed, when problems seem insurmountable, when anxiety or stress or fear dominate your thoughts, you can step back and remember the cosmic web. You can remember how vast the universe is, how ancient, how indifferent to your personal struggles. And somehow, this makes your problems feel more manageable. Your worries are real to you, of course. They matter in your life, in your experience. But they're also temporary and local and small. They'll pass. Whatever you're anxious about today will likely be forgotten in a week or a month or a year. And even if it's not forgotten, even if it has lasting consequences, those consequences play out on human scales, on your personal timeline, which is brief and finite in cosmic terms. The universe will continue regardless of what happens to you. The cosmic web will keep evolving. Galaxies will keep flowing along filaments. Stars will keep forming and dying. The great dance of matter through space and time will continue completely unaffected by your personal triumphs or failures. And there's something oddly comforting in that. You're free to live your life without the weight of cosmic significance. You don't have to matter to the universe. You just have to matter to yourself and to the people around you, to the small sphere of influence you actually affect. You can let go of the pressure to be cosmically important and simply focus on being human, on living your brief life as well as you can, on finding meaning and joy and connection in the small-scale human world you actually inhabit. But there's another side to this perspective. If you're cosmically insignificant, so is everyone else. Every human who's ever lived, every civilization that's ever risen and fallen, every empire and achievement and artwork and idea, all of it is small and temporary in cosmic terms. The differences between us, the things we fight about, the boundaries we draw and defend, they're even more insignificant than our individual lives. From the cosmic web's perspective, there's no meaningful difference between nations or ethnicities or religions or any of the categories we use to divide ourselves. We're all humans on one small planet, sharing one brief moment in cosmic time. We're far more similar to each other than we are to anything else in the cosmos. We're the same species made of the same atoms, shaped by the same evolutionary history, living in the same cosmic context. Perhaps if more people truly internalized this perspective, truly understood the cosmic web and our place in it, we might treat each other better. We might recognize that our differences are trivial compared to our commonalities, that our conflicts are petty in cosmic context, that we should work together rather than against each other because we're all sharing one small world in an incomprehensibly vast universe. This is the lesson of the cosmic web. We're part of something vast and beautiful and ancient. We're connected to structures stretching across billions of light years through billions of years of cosmic history. And yet we're also small and brief and local, living out our days on one tiny world, making our own meaning in a universe that doesn't provide meaning for us. Both perspectives are true simultaneously. We're cosmically insignificant and personally significant. We're tiny parts of something vast. We're brief moments in an ancient story. We're connected to everything and isolated in our small corner of space and time, holding both perspectives at once, understanding both our smallness and our connection to the larger cosmos. This is wisdom. This is what the cosmic web teaches us if we're willing to listen. As we bring this journey to a close, let's appreciate what we've discovered together. We started with a simple observation that the night sky appears randomly scattered with stars. We learned that beyond those stars are galaxies, billions of them, and we wondered how those galaxies are distributed through space. We discovered that galaxies aren't randomly distributed. They're organized into a cosmic web of filaments, voids, and nodes, a structure so vast that it extends throughout the observable universe. We learned how this structure formed through gravity and dark matter over billions of years, starting from tiny quantum fluctuations and evolving into the complex pattern we observe today. We traced our location within this structure, understanding that we're embedded in a filament, part of Laniakea, moving through the cosmic web along with billions of other galaxies. We learned that we're being pulled toward the Great Attractor and pushed away from the Dipole Repeller, flowing along currents of matter that span hundreds of millions of light years. And we reflected on what all of this means for our understanding of the universe and our place in it. We're part of something vast and ancient and beautiful. We're connected to the largest structures in existence through the atoms we're made of and the laws of physics we obey. And yet we're also small and brief, living out our tiny lives on one small planet in one ordinary galaxy among billions. The universe has a hidden structure, and you're inside it right now, embedded in it, moving through it, part of it in the most fundamental way. The atoms in your body were formed in stars that formed in galaxies that formed along the filaments of the cosmic web. You're not separate from the cosmos. You're a part of it, temporarily organized into the pattern we call human, briefly aware of your own existence and the existence of the vast structure surrounding you. Tomorrow the sun will rise over your small part of Earth. Your day will begin with its tasks and concerns, its joys and challenges. You'll navigate the human-scale world of relationships and responsibilities, of plans and problems. And the cosmic web will continue, vast and ancient and indifferent, organizing matter on the largest scales, evolving according to its own inexorable logic. But tonight, rest here with this cosmic perspective. Let the vastness wash over you. Feel your connection to something larger than yourself. Understand that you're part of the universe's grand architecture, a small but real component of the largest structures that exist. You've learned something profound tonight. The universe has revealed one of its deepest secrets to you, and as you drift towards sleep, let that knowledge settle gently in your mind. You're part of the cosmic web. You always have been. You always will be, even after you're gone, as your atoms return to the cosmos, and perhaps eventually become part of other stars, other planets, other structures along the filaments of the eternal cosmic web. Sleep now. Rest peacefully. The universe holds you gently in its vast structure. You're home. You've always been home in the cosmic web that connects everything. Good night, cosmic traveler. Dream of filaments and voids, of structures stretching across billions of light years, of your place in the grand architecture of the universe, or dream of nothing at all. Just sleep deeply and peacefully. The cosmic web surrounds you. You're part of it, and that's something beautiful to carry with you as you drift into sleep. Good night.